So it is my honor this morning to introduce to you the Machine Learning Best Student Paper Award, which is awarded to Kelvin. Kelvin is a PhD student at the University of Sydney and Data 61, a CSIRO in Sydney, Australia. He also worked at National ICT Australia as a machine learning research engineer before he started his PhD. His background is in mathematics and statistics, but also in music, because he's also a musician in a small band, a small acoustic band. His main current research area is in approximate Bayesian inference and learning, and his paper is about hyperparameter learning for conditional mean embeddings, which are about complexity bounds. So be ready for some RKHS stuff and some learning theory. I think you should be awake this morning because it's going to be a tough talk. I think I read the paper and it's not an easy read. Please welcome the speaker, Kelvin.
Keep it simple for a complicated paper. So, good morning everyone. So, my name is Kelvin. I'm from Sydney, Australia, which probably means I'm the most jet-lagged person ever in this room right now. I woke up really early today. So, if you look at the title of my talk, it actually spells out the story of how this work came about. So, I was looking into conditional mean embeddings for a while now, and I really like the elegant mathematical theory that it brings. It's a really sort of holistic framework for doing probabilistic inference, the whole thing. So I thought it was really cool, and as I looked deeper into it, I realized that conditional mean embeddings are naturally suited for probabilistic classification in a multi-class setting. And I thought that was kind of rare and strange, right? Usually when you have classification, it starts off binary as a natural thing first. And then you might want to extend that to a multi-class by, combining multiple binaries or doing some sort of smart sort of extension to that. So it's kind of rare to have something that's sort of just naturally multi-class. So I thought that was interesting. Why isn't anybody looking at this? So I dived into it deeper and I realized the problem. The problem is that conditional mean embeddings have hyperparameters, and these hyperparameters are super difficult to learn. So one of the things today that I want to get across to everyone is just why hyperparameter learning is such a critical problem for conditional mean embeddings. And so in order to sort of address this problem, I looked into different things, and then I found learning theory, which really helped with dealing with this problem. And the part of learning theory that deals with this problem is this thing called random empirical complexity. So we'll sort of talk about this in a high level, and this is what I sort of want to get across today. So in order to get that all across today to all of you guys, I want to start off with a simple exercise. So here are 3 decision probability maps. Imagine you're trying to do probabilistic classification in a multi-class setting. So here are all your data points, probably easier to see on this one. You've got 3 classes here, red, green, and blue. The data points are the same for everything. The only difference is the 3 has different models. So your goal, of course, is to predict 3 decision probabilities. One for, at each point, how likely is it to be red, green, or blue? And so since there's only 3 classes, it's very convenient because we also have 3 color channels, RGB, so you can visualize it that way. You can use each of the color channels to visualize the probability output. And for each point, you put your prediction as the one with the maximum probability. So if red has the highest probability, you predict red, of course. So we also drew the decision boundary line for where that prediction changes. So that's what this picture is, visualizing your model's predictions for 3 class classification. So you've got 3 models here, A, B, or C. Which one would you guys pick? A? Yeah, no one says it other than. So if you pick anything other than A, you're crazy, right? Of course you pick A, right? Why would you? So this model, of course you pick this because it has the best data fit, right? Number 1. Number 2, it doesn't look too complicated. It has sort of the right complexity. It looks elegant. It's like a nice spiral, right? It's a good pattern to have. Right, so this is an easy one to pick. Let's look at another situation. So what about this one? So here I also included the test data. So maybe it's a bit hard to see far away, but there's actually stars and circles in the scatter plot. The idea is that they're randomly split, so it's all across each other. You can sort of see a smudge of green and blue dots here. Oh, there's this merge of green and blue dots here, and then red over there. So that's the situation. Which one would you pick now? Huh? who would pick A? Who would pick B? Yeah, okay. Who would pick C? Yeah, of course. So you pick B over here, right? And that's because what we really care about is generalization performance. Right? So over here, I included test accuracy over here. So you can see on these two, the test accuracy is 56. You know, not that good. The middle one is 73, which is better than the other two. And actually, this data set, I think a lot of you will recognize it, right? This is the famous iris data set that everybody would have seen in the first year statistics. So you might remember that this data set used to be 4-dimensional originally, but if you take the first 2 dimensions, the data set actually becomes not separable at all. So it's not just not linearly separable, it's not separable at all. Because at the same point, you can have the different classes. You can have the same point and there's a green dot there and a blue dot there as well. So pretty much 73.33 is the best we can really do over here. What I'm presenting over here is literally just the common topic of overfit, right? There's nothing special. We've already seen this so many times, so many ways to deal with this. We've saw so many great ways. Things like cross-validation, they must work over here, right? With the stepper techniques, right? So I thought that would work, but unfortunately, as I tried it out, this is what happens. So the common hyperparameter training algorithms you have for conditional mean embeddings are these. So you have median lane heuristic. Median lane heuristic works by you have all the data points, you find the pairwise distance between all the data points, and you find the median of that. It's a very simple algorithm. So there's 2 problems with that. Number one, it can only be used to set length scales. So just then I showed you an example of a length scale parameter, but there are also other types of hyperparameters. And if you use this technique, you can't learn that. So that's number one problem with this. Number two is that it does not make use of any of the label information. So it does not really know, whether that point is red, green, or blue. It doesn't make use of that. So it doesn't even have the critical information to do well. So that's how it plays. And the other two is cross-validation, our favorite. So for cross-validation over here, it works much better. You can see the middle one also has 73.33%. Pretty good, just like the one before. And it performs not bad. But the problem is, if you look at the performance here, you sort of, feels weird about it, right? Like if you pay attention to this, what's this thing over there? What is all this weird gray area? So why is it doing that? Why isn't it modeling that area well? So of course we know cross-validation it minimizes the loss on some validation sets. Maybe across many flows, but in the end, it has to be minimizing the loss on some data. We don't have any data on these parts. So of course, our cross-validation algorithm is not going to care about it. It's going to leave it alone. Never had the info about it, so it's just going to do whatever there. So you can't blame cross-validation for that. Right? So over here, you might say, I'm being unfair. Right? You never had the data over there. Who says that this is a bad model? Right? You model this part well. That's all your data. That's all your test data as well. So you shouldn't be complaining. Right? But I would argue that for such a simple scenario, this is a toy example, right? You would want your learning algorithm to be able to identify such a simple pattern. So what that means is, for example, if you want to transform between 2 different distributions, and that transformation is hard. So for example, people doing Bayesian inference will know marginalization integrals are super difficult to do. So this step is super hard. There's a mountain there, you can't do it. So what do? You can embed them into the reproducing kernel paper space. And then in this space, most of the probabilistic operations are linear. So easy linear operations, and then you transform them back. Now the problem is this is too good to be true. This step is actually a bit hard. It's not as hard as that, but it's still hard. So what do you usually do? Well, the thing is, instead of actually doing that, we realize that most of the time when we want to do inference, we don't really need the whole distribution, right? We need some sort of expectation. So instead of finding the distribution, if you can formulate your inference problem as just an expectation of any function, then you can just do it in a product and you're done with the thing. And that's actually quite flexible. Moments are expectations. There are a lot of things that we want to find out are expectations. So you don't actually need to go through this hard step, most of the time, as long as you can do this. So here's an analogy that sort of shows you, how this so-called works. So, if you've got Charlie Brown who wants to become Superman, and he can either train hard, work hard, level up, not gonna happen. So what he can do, you can have a crazy scientist extract your DNA into the space of DNA, so you can do some DNA manipulation, and you can transform them back. Now, I said this part is hard, so instead, you realize that a lot of the insights that you get from, a person, you can probably get the analysis from the DNA as well. So that's what I mean by you can just get it from their expectation. You don't really need the actual human here, right? You don't get to talk to them, but you can analyze them. Let's go to the conditional mean embedding now. So for conditional mean embedding, it works by embedding a conditional distribution. So conditional distribution here, you've got the input x over here that you're changing, and this is a distribution that's changing as you change your input variable. And you can embed these three distributions into the reproducible kernel Hilbert space. And the idea is that as you sweep out this x, you sweep out the entire family of mean embeddings over here. Now, how do we get those empirical estimates? So if you have samples, how do you get estimates of these things? So that's another sweep that's hopefully close to the blue one. So in practice, you don't get something like this. You don't get samples that are just like, nicely already there for you. You get a joint sample everywhere. So the nice thing about conditional mean embedding is that it can actually use the joint sample and estimate the entire strip volumes. And so it's a consistent estimate of the entire probability distribution. So thank you very much for listening.